Pretty much every astronomy professor will tell you that the most important graph in all of astronomy is the HR diagram. And this is what it looks like. This is one sort of version of it. And it's a pretty complicated diagram, to say the least. And so what I want to do over the course of this lesson is just kind of break it down and see how you've actually seen a lot of the pieces that go into making this diagram what it is. Before we get into it, though, I just want to highlight what the units or the axis, okay, because these are things that we've already seen a little bit of. This axis here is luminosity, and you can see the other axis is temperature. So let's just revisit this question of like temperature and how it impacts things by looking back at this simulation. If you remember back when we learned about black bodies, we said like basically anything can act sort of like a black body, even you and I, so that if we have a temperature, we give off light. But there's no real true black bodies in the universe. The closest thing we have is stars. So stars really do act like black bodies, pretty close. And one of the ways that we can see this connection between temperature and luminosity is by even just looking at a heated nail. So let me go back. You probably remember seeing this as the temperature increases on this nail, right? You can see the temperature is like 1,000 Kelvin, right? We can start to see it glowing in the red and yellow parts of the spectrum. And then as the temperature goes up, right, it became more kind of whitish and brighter. And that's the thing I want to focus on. So let's look at this part of the graph right here. This here showing like the total amount of light being given off. Remember, we said luminosity is a way of talking about all the light over the entire spectrum that's being given off by a star. So let's just compare, and this is a nail. I realize this is not a star, but it's the same physics that controls the light being given off by a nail and the light being given off by a star. So when we have a cooler star, so a low temperature star, you see this luminosity. If I were to say the luminosity is the area under this curve, right? So if I could kind of color it in, it'd get messy fast, right? But here's kind of the total area under the curve when we have about 1,000 Kelvin. Okay, and then I'll change colors. And now when we go to a higher temperature, let's go to like 2,000 Kelvin. I won't even make it there. 1,500, how about? See how much more area there is under there? The luminosity is so much higher, the total light being given off across the whole spectrum. Okay, so we can just color that in. See how much more? Woo, so much more luminosity. Okay. So I could, in principle, I could see this another way. Let me show you another way. We saw this kind of graph too. We saw this simulation in an earlier lesson. The temperature is here at 3,000 Kelvin. So my scale, this is luminosity again. It's called flux here, but this is luminosity. And as I turn up that temperature, remember the total area under the curve, which I can even highlight here, goes up really dramatically, like extremely fast. And if you remember, we even had an equation for it that the luminosity depends on temperature to the power of 4. So that means if you double the temperature, you go from 4,000 to 8,000 Kelvin, right? That means the luminosity goes up by a factor of 16. So it's an extreme dependence on temperature. Now, that's really the heart of an HR diagram. Because what is an HR diagram? Remember, the HR diagram was 2 scales, right? Or 2 axes. And I'm going to draw it right here so you can see it. The HR diagram was luminosity on one scale. Okay, luminosity. And the other scale was temperature. Now, the tricky thing about an HR diagram, temperature, and this is more for historical reasons than anything else, is like low temperature is over here. So let's just put 1,000 Kelvin over here. And then we'll put like 30,000 Kelvin over here. Okay, so they flip the scale. So it increases, or I guess you could say it decreases to the right. Okay, and again, that's just the way astronomers used to make it. And here you could say this is like 1 solar luminosity. That's like how much light the sun gives off. And here is like the solar temperature right here. Let's say about 5,000 Kelvin. Okay. Now, from what we just said, this is really kind of intuitive, I guess I would say. When you have a low temperature, so 1,000 Kelvin, you have a low luminosity, right? And when you have a higher temperature, you have a higher luminosity. And when you have a really high temperature, you have a really high luminosity. Now, if you're a math person, you might be like, well, wait a minute, you said it depends on temperature to the fourth. Why isn't this curved? Well, these are actually logarithmic scales. Again, you can ignore me if you're not a math person, but if you are, this scale is actually logarithmic. So this would be 10 solar luminosities. This would be 100. And so that's why it's a straight line. But what we see is that in general, in an HR diagram, you would expect stars to follow this pattern, that they would kind of be in a roughly straight line along here, relating their luminosity to their temperature. So that is the starting point, and that's actually the key element of the HR diagram. It is called the main sequence. The main sequence. And if I go back to that drawing I showed you at the beginning, you can see that right here, the main sequence. Boop, boop, boop. You see it goes all the way from high temperature, high luminosity, down to low temperature, low luminosity. All right, and we'll explore some of the other elements of the main sequence in the next video.